Hello everybody, welcome back to G4 Labs IB Physics, and today we're going to be doing momentum and impulse. So I've been gone for like a couple months. Sorry about that. I've been busy with college apps and school, so yeah. Okay, so what is momentum? And I'm sure you've heard a lot about momentum if you played sports, or maybe if you drive a car, and maybe you've heard that on the road, trucks have more momentum than cars usually. And what we're gonna see is that this is the case because momentum can kind of be thought as strength of motion. So how do we quantify strength of motion? Well, a French mathematician, French should be capitalized, by the name of Rene Descartes, originally quantified it as P is equal to mv, where P is momentum, V is velocity. And so clearly it's a vector quantity, as velocity is a vector quantity, right? And from this definition, we can see that objects with very high mass are going to naturally have a higher magnitude of momentum. If a truck and a car are moving at the same velocity, then the truck's going to have more momentum because it has more mass. And the same goes for objects moving at high velocities. And so the unit is going to be kilogram meters per second. And why? It's going to be that because P is equal to mv, right? So M, that brings in kilograms, V, that brings in meters per second, kilograms times meters per second, kilogram meters per second. Cool, right? All right, so problem number one. A truck that weighs 2,000 kilograms is moving at 10 meters per second. What's its momentum? I'll give you a second to do that. Okay, so we just apply the definition of momentum. P is equal to mv, and we get P is equal to 2,000 times 10, which is 20,000 kilograms meters per second. Okay, another problem. So oftentimes an object can have a change in momentum after collision. A ball that weighs half a kilogram moving at 10 meters per second hits a car, and the ball bounces back at 6 meters per second. What was the change in momentum of the ball? Oh, for this problem, you need to assume that the ball, when the ball is moving towards the cart, I guess, that's the positive direction, by the way. Okay, so we solved this one by comparing the momentum before and after the collision. So the change in momentum is going to be final momentum minus the initial momentum. So when we plug in our values, we get 0.5 times negative 6. It's going to be our and when we subtract 0.5 times 10, right? It's going to be negative 3 minus 5, gives us negative 8 kilogram meters per second. So that's our change in momentum. All right, so what is the conservation of momentum? The conservation of momentum basically states that the momentum of a closed system is always conserved unless the system is acted upon by an external force. And so what this means is that in systems with multiple objects, momentum's neither going to be created, or even two objects, momentum's neither going to be created nor destroyed. It's going to be transferred. Okay, and building on that, moving on to collisions and explosions, since the momentum of an isolated system always stays the same, that means no matter what, the momentum must stay the same after two objects collide. And well, assuming these objects are part of the isolated system. And so adding on, there are two categories of collisions actually. So elastic and inelastic. For now, you can think of elastic collisions as where the objects don't stick together after the collision, like in a pool ball where like you hit a ball and then it pretty much transfers like all its momentum to the other ball, right? And then there's also inelastic collisions where the objects do stick together, like a car crash, for example. And so most collisions in real life can be a mix of both, and in explosions, which are isolated systems, right? Momentum's also conserved. Okay, so a ball weighing 0.1 kilograms moving at 1 meters per second hits another ball weighing 0.5 kilograms at rest. The original ball comes to rest after the conclusion. What is the velocity of after the collision? Wow, okay. What is the velocity of the second ball afterwards? Okay, pause the video. You can try this one yourself. Okay, let's go. So this is an inelastic collision, and we can solve the problem by applying conservation of momentum with the system being the momentum of the two balls. So how do we apply conservation of momentum? Well, in order for the total momentum to be the same, that means the momentum of both balls initially summed up has to equal the momentum of both balls finally after they collide and summed up, right? Oh, that should be P1F and P2F, by the way. Yeah, I ignore the mistake there. And so when we plug in our values, we're going to get 0.1 times 1 plus 0 because the other ball is initially at rest, right? And equals to 0 because the first ball comes to rest after hitting the second ball times 0.5 times V, which is nice because we're solving for v and it's already isolated. So now we just divide by its constant, which is going to be 0.5. So 0.1 divided by 0.5, 0.2 meters per second is the velocity in the same direction that the original velocity was, because it's positive. Okay, so we got another problem, right? Car weighing 1,000 kilograms moving at 5 meters per second hits a truck weighing 5,000 kilograms moving at 2 meters per second in the opposite direction. Okay, so in other words, they were coming towards each other. So after the collision, the two vehicles stick together. So what's their velocity going to be afterwards, where positive is the direction of the car? Okay, so this is an inelastic collision, right? And so we can solve this problem by applying conservation of momentum with the system being the momentum of the two vehicles, just like before, right? So what's going to happen here is that the first side of the equation is the same, right? We get 1,000 times 5, which is the initial momentum of the car, plus 5,000 times -2, because the truck was going the opposite direction, coming towards the car. And so what we're going to find is that since the two vehicles stick together, we have to represent this as v, because once they stick together, they have the same velocity. So we can actually we can factor out velocity and write it nicely like this. So v is v times 1,000 plus 5,000, because the system afterwards is going to have the mass of the two vehicles combined, right? And so once again, we already have our v isolated. So 6,000 v is going to be equal to 5,000 minus 10,000, right? And if you divide, that's going to be -5,000. If you divide -5,000 by 6,000, you're going to get -5.6. So that means our velocity afterwards is going to be -5.6 meters per second. And how you can interpret this is that because basically the truck has more momentum and it's going in the opposite direction, they're gonna collide, stick together, and they're gonna go in the opposite direction that the car was going. They're gonna be traveling the direction of the truck after the collision. Okay, so now moving on, what is impulse? So impulse is basically like a change in momentum, right? And so when a force is delivered for a certain amount of time, we call it an impulse, right? And so this whole concept is also known as the impulse momentum theorem. And impulse is usually notated as J, and units are Newton seconds, because, well, you'll see why. This is because the formula for impulse is J impulse is equal to force times time, right? So Newtons times seconds, Newton seconds. Okay, yeah, and not to be confused with energy, by the way. So if you can measure the force an object experiences over time, you can actually calculate the impulse an object experiences through that time. And in this graph, we see that a force of 30 newtons is applied for 5 seconds, right? So summing the area of the graph will get us the total impulse delivered to the object, which is 30 times 5 is equal to 140 newtons per second, right? Area under the curve, right? It's cool. It's an application of calculus, actually. So, actually, I made a little mistake here. So 30 times 5 is 150 newtons. Actually, wait, no, it starts from t is equal to 1, right? So it'd actually be 120 newtons per second, because the force of 30 newtons is applied for 4 seconds. All right, yeah, please ignore the errors. Okay, so a cart weighing 5 kilograms starts moving at 4 meters per second after Billy gives it a short push. If the push lasted half a second, what was the average force applied to the car? Okay, so here's a free body diagram while the car is getting pushed. In this case, it's just the applied force, as we're ignoring friction, right? So the cart was initially at rest, and it started moving at 4 meters per second, which means we know the impulse, right? It's a change in momentum. And so it was initially at 0 momentum, and the momentum afterwards was 20 kilograms meters per second, because 5 times 4 is 20. So that's the change in momentum. Now we can just apply the formula for impulse, because we already know the amount of time the push lasted, which is half a second, right? So 20 is going to be equal to half times F, which is 0.5 times F, which is just, F is the force, right? So now divide both sides by 0.5, we get F is equal to 40 newtons. So that's the force Billy applied. Yeah, so more on impulse, right? Impulse and momentum are very applicable in our daily lives, right? So, for instance, the crumple zone of a car utilizes impulse and momentum by significantly lengthening the time span of the collision, right? And so the change in momentum of the car is going to be the same either way, but think about the formula, right? The impulse is equal to the force times the time, right? Since the collision takes place over a much larger of time, and in order for the strength of the momentum, the change in momentum to be the same, the average force the car experiences has to be significantly lower mathematically, right? And that's obviously a lot safer for us people inside the car. And in general, materials that can help lengthen collisions prove to be a lot safer than materials that don't, right? And so this is why you'd rather trip and fall on grass than concrete, right? Grass is much softer, and even a slightly longer collision can make a difference between whether you break your bone or not, I guess. Yeah. Okay, so problem number 6. We got a little challenge problem here. A rocket weighing 100,000 kilograms, traveling at 1,000 meters per second, 60 degrees to the horizontal, splits into two parts. One weighing 40,000 kilograms and the other weighing 60,000 kilograms. So if the two parts deviate 20 degrees from both sides of the original course, what is the velocity of each one? So assume the heavier one is the one that went below the original trajectory. Okay, so this is kind of like an explosion. We can apply the conservation of momentum principles. The rocket courses at an angle. The very first thing we want to do is figure out the horizontal and vertical component momenta or velocity. So we're going to get that 100,000 times 1,000, 10 to the 8th kilograms meters per second. And the components here, 10 to the 8th cosine 60, so 5 times 10 to the 7th kilogram meters per second, 10 to the 8th cosine 60, root 3 over 2 times 10 to the 8th. And we know that momentum is conserved totally, so that means the horizontal and vertical momentum before must be the same afterwards. We know that the parts go 20 degrees off course after splitting, so that makes the angle to the horizontal 40 degrees and 80 degrees. So, and from splitting components of the new runs, right? New rockets, we get these systems, or this system, right? 60,000 V1 cosine 40, 40,000 V2 cosine 80 is going to have to equal to 5 times 10 to the 7th kilogram meter per second, right? Because the total momentum of the system has to be conserved, these two have to be equal. Okay, and yeah, as you can see, the bottom one's just for the vertical component. Yeah, so all we have to do is solve for V1 and V2. Okay, so this is a bit of a tedious solution. If you want, I'll wait here a bit and you can take a look at exactly how you solve the system. So essentially, you do it by like substitution, I believe. Yeah. So you find V1 or V1 in terms of V2, then you got to apply that back into one of the equations, and that way you can solve for V2, which ends up being 1330 meters per second, right? And so once you get that, you can plug that back into V1, the V1 formula for V1 you got in terms of V2, right? And you're going to get 887 meters per second. So yeah, and by the way, V1 is 40 degrees north of east, and V2 would be 80 degrees north of east. Yeah, it's a bit messy. There's a lot of playing around with trig, but should be doable. Yeah, and by the way, this should probably be like a very high mark question on an IB test. So yeah, don't worry. Alright, so to review, today we learned that momentum is kind of like strength in motion and that it's conserved in a closed system. And we also learned that impulse is effectively a change in momentum, and these are both very applicable concepts in our daily lives, such as in a car crumple zone, for example. Alright, thank you so much for watching this video. I'm sorry for postponing this video so much. So yeah, and be sure to check out our IB Comp Sci, IB Bio videos as well. Thank you. Bye.